Right now, in this high-tech facility, 40,000 bamboo strips are 8 degrees away from becoming worthless. One temperature mistake, $15,000 lost per hour. This isn't craftsmanship. This isn't tradition. This is mass production at industrial scale, where precision is measured in grams and seconds determine millions. Welcome inside a factory you've never seen before. Bamboo, the fastest growing plant on Earth. 3 feet in 24 hours. In traditional settings, it's hand-cut, sun-dried, and crafted into simple products. But in modern manufacturing, it's processed at massive scale. 20 tons per day, transformed into engineered panels that compete with hardwood flooring. This facility operates nonstop, 3 shifts, continuous production. The bamboo must arrive within 72 hours of harvest. That window is critical because bamboo isn't wood, it's a grass. And it behaves completely differently under industrial processing. High starch content, unique fiber structure, dramatic moisture fluctuations. The factory has one production cycle to transform fresh bamboo into stable, engineered material. And that transformation depends on decisions made at 3 critical points. From start to finish, 8 major stages. But only 3 contain decisions that can halt production and cost millions. Let's break them down. Stage 1. Reception and quality grading. Diameter, age, visual inspection. Stage 2. Cutting and splitting. Cylindrical bamboo becomes strips. Stage 3. Carbonization and moisture control. First critical decision. Stage 4. Fiber separation and mechanical processing. Stage 5. Adhesive application and layering. Second critical decision. Stage 6. Hot pressing and compression. Third critical decision. Stage 7. Surface finishing and inspection. Stage 8. Packaging and storage. Everything flows in sequence. But stages 3, 5, and 6 determine profit or catastrophic loss. Let's examine what's really happening at each decision point. The bamboo strips enter the carbonization chamber. Thermal treatment at industrial scale. Target temperature, 190 degrees Celsius. Duration, 48 hours. Carbonization serves 2 functions: sugar removal and color standardization. But here's what most people don't know. Carbonization isn't about color. It's about chemistry. At 190 degrees, the natural sugars in bamboo caramelize and break down. The bamboo turns from pale yellow to rich caramel brown. But those sugars are the reason bamboo decays. They attract termites, promote fungal growth, and destroy durability. Remove the sugars, and bamboo becomes as durable as hardwood. The margin for error, 8 degrees. If temperature drops to 182 degrees, sugar removal is incomplete. The final product attracts insects and fails durability testing. Rejected. If it rises to 198 degrees, the fibers begin to char, structural integrity collapses. The material becomes brittle, unusable, 8 degrees. That's the difference between premium flooring and industrial waste. From an engineering perspective, this is controlled thermal decomposition. But this is where process stability is tested, because carbonization also drives moisture content down to a critical range, 6 to 8%. And here's the part that changes everything. This moisture level isn't just a target. It's the foundation for every decision that follows. If the bamboo exits carbonization above 10% moisture, the adhesive in stage 5 won't bond. Delamination occurs. Product fails. If it drops below 4%, the bamboo becomes overdried. It cracks during hot pressing. Total loss. The factory monitors both variables in real time. Embedded sensors at 12 points in the carbonization chamber. Temperature, moisture, continuously tracked. If any sensor detects deviation, automated steam injection or ventilation adjusts conditions within 30 seconds. This level of automation exists because at 20 tons per day, 1 hour of incorrect carbonization affects 800 kilograms of material. At premium pricing, that's $15,000 lost. Every single hour, 1 deviation here, and the entire day's production becomes biomass fuel. The carbonized bamboo moves to adhesive application. This is where individual strips become engineered panels. The adhesive is phenol formaldehyde resin. Food safe, waterproof, heat activated. Application rate, 120 grams per square meter. Margin of error, 5 grams. This decision is often underestimated. That's $1 million mistake. Here's what's happening at the molecular level. The resin must penetrate the bamboo fiber to a depth of 0.3 millimeters. 0.3 millimeters. A human hair is 0.07 millimeters thick. The resin must penetrate 4 times deeper than a human hair. Too shallow and the bond is weak. Too deep and the resin bleeds through to the surface. If application drops to 115 grams per square meter, resin coverage is incomplete. During hot pressing, gaps form between layers. The panel delaminates under load. Rejected. If it rises to 125 grams per square meter, excess resin pools on the surface. During pressing, it squeezes out and creates defects. Surface finish is ruined. Downgraded or scrapped. 5 grams per square meter. That's the difference. But here's what makes this decision even more critical. The adhesive reacts with moisture in the bamboo. If the bamboo entered this stage at 10% moisture instead of 7%, the chemistry changes completely. The resin curing time accelerates. It begins to cure before pressing. Pre-cured resin doesn't flow under pressure. The bond fails. This is why the carbonization decision matters. One error upstream creates a cascade downstream. In industrial practice, this is where mass production meets chemistry. The factory uses precision spray nozzles controlled by flow meters. Application rate monitored continuously. Real time. Adjustments compensate for moisture variations from the previous stage. At 800 panels per day, a 5-gram deviation affects 60 panels. At $200 per panel, that's $12,000 lost. Every single day, the layering follows immediately. Adhesive-coated strips stacked in alternating grain directions. Cross-lamination creates dimensional stability. Assembly window, 6 minutes. After 6 minutes, the resin begins initial cure. Pressing becomes ineffective. Automated stacking robots. Precision timing. 0 human error. Because this decision determines success in the next critical stage. Hot pressing. The stacked bamboo enters the hot press. Temperature, 140 degrees Celsius. Pressure, 300 tons per square meter. Duration, 12 minutes. This is the moment where everything succeeds or fails. Hot pressing serves 3 functions. Resin curing, layer bonding, dimensional compression. At 140 degrees, the phenol formaldehyde resin undergoes thermosetting. The chemical bonds become permanent, irreversible. Temperature and pressure must be perfectly synchronized. If temperature is too low, 135 degrees, the resin doesn't fully cure. The bond remains weak. Under load testing, panels fail. Entire batch rejected. If it exceeds 145 degrees, the resin cures too quickly. Internal stresses develop. The panel warps after cooling. Unusable. And pressure control is equally critical. At 300 tons per square meter, the bamboo compresses from 18 millimeters down to 15 millimeters. This compression is permanent. If pressure drops to 280 tons, compression is incomplete. Panel thickness exceeds specifications. It won't fit standard installation systems. Rejected. If it rises to 320 tons, the bamboo fibers crush. Structural strength is lost. The panel becomes weak and prone to cracking. From an engineering perspective, this is thermomechanical processing under extreme conditions. The factory uses hydraulic presses with computerized control. Temperature monitored at 8 points across the press platens. Pressure measured continuously with load cells. If any parameter deviates by more than 2%, the press adjusts automatically within 3 seconds. This precision exists because at 800 panels per day, one failed pressing cycle affects 66 panels. At $200 per panel, that's $13,000 lost. In 12 minutes, the panels exit at 140 degrees. They must cool to 40 degrees within 20 minutes to prevent thermal warping. forced air cooling, controlled gradient, precision timing. Every upstream decision is visible in the final product here. If carbonization moisture was wrong, adhesive didn't bond. Panel delaminates. If adhesive application was incorrect, surface defects. Panel downgraded. If hot pressing failed, panel warps, cracks, or fails strength testing. Each decision compounds. One error creates a cascade of failures. After cooling, every panel undergoes rigorous testing. Visual inspection for defects. Dimensional measurement to 0.1 millimeter tolerance. Moisture content verification, 6 to 8%. Mechanical testing. Bending strength, impact resistance, delamination force. The rejection rate reveals the effectiveness of every upstream decision. Industry standard, 5% rejection. This factory, 1.8%. That's the result of precision control at 3 critical decision points. But here's the economic reality. At 1.8% rejection, the factory loses 14 panels per day, $2,800 in direct loss. At industry standard 5%, the loss would be 40 panels per day, $8,000. The difference, $4,500 per day, over $1.6 million per year. That's the cost of imprecise control at critical decision points. And that's why automation, sensors, and real-time monitoring aren't optional in modern manufacturing. They're the difference between profit and catastrophic loss. 3 decisions, 3 variables, 3 points where millions are made or lost. Carbonization, 190 degrees Celsius, 48 hours, moisture to 7%. 8-degree margin. 1 mistake and sugar removal fails. Adhesive application, 120 grams per square meter, 6-minute assembly window. 5-gram margin. 1 deviation and bonding fails. Hot pressing, 140 degrees, 300 tons pressure, 12 minutes. 1 error and panels warp or delaminate. This is modern manufacturing at industrial scale, where precision meets mass production, where bamboo transforms from grass to engineered material that rivals hardwood, and where one wrong decision can cost millions. That's the reality inside a factory you've never seen before, where grass becomes engineering, where 8 degrees changes everything, and where millions are made or lost in 12 minutes.